Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about the probability density function. The goal is to define probability density and describe its properties. The prerequisites are continuous random variables, and I forgot to put there that you should also be familiar with the concept of derivative. That's going to be really important at an intuitive level, and also it would be useful if you remembered how to compute derivatives, because we're going to do that quite a bit. Okay, so we already have a tool for dealing with continuous random variables, which is the cumulative distribution function. So remember that continuous random variables are defined so that the probability that they are in an interval or in a union of intervals is well defined, and that's what we usually are interested in. And the cumulative distribution function gives us that. The cumulative distribution function, or CDF, I'm going to say CDF from now on because, as you can see, cumulative distribution function is quite a mouthful. The CDF is the CDF at a point A is the probability that the random variable is smaller or equal to A. So let's take a look at the picture. This is the CDF of a certain random variable. Remember that CDFs always go from 0 to 1. And if we're interested in the probability that the random variable is, for example, here, smaller than 0.5, then that's just the value of the CDF there. If we're interested in the probability that it's smaller than 2.5, then it's that value, in this case 0.6. Okay, the CDF gives you that too. And if you want the probability that it's in the interval in between, you just subtract the CDF values at those points. So the CDF gives us all the information we want to know about the random variable, but it's a little bit clunky, right? Because if we're interested in what is going on in this interval here, or even more locally, then we have to subtract CDFs, and at the end of the day, the CDF captures the behavior of the random variable up to a certain point, so like very globally. So here what we're going to want to do is define a tool that allows us to describe the local behavior of the random variable. Okay, so the CDF is a global quantity, and we want to characterize local behavior. To do that, we're going to use the concept of density. So first, let's describe intuitively what the density is. Here I've drawn some arbitrary density. So you have to think of the random variable as being distributed here. So it can take random variables on this real line. And now a density tells us the probability that the random variable is in a small interval, very, very local interval around a point A. And what we're assuming is that the interval is super, super narrow. So this is super, super narrow, so that the probability that the random variable is here in this interval is given by some constant quantity, which is the density at that point. And remember, we're taking the interval as narrow, like in the limit where epsilon goes to 0. The probability of the random variable being in that very narrow interval is going to be the density multiplied by the width of the interval. This is exactly the same way that we define density for mass. Like if you want to calculate the mass of an iron rod or something, what you're saying is the density of the rod is such that when I go to infinitesimal pieces of the rod, I just have to multiply by the length of the piece, and that gives me the mass. Or when you're considering a position that changes over time, if you look at the position over a very, very, very short interval, then the velocity gives you the change of position, right? You multiply the velocity by the length of the change of position. That gives you how the position changes in a very infinitesimal point. Okay, so this is basically a generalization of those concepts of velocity or density to the case of probability. Let's be a bit more mathematical, now that hopefully we have provided some intuition. The probability density at a point A is the limit, when epsilon goes to 0, of the probability that the random variable is within an interval of length epsilon that starts at A minus. Here it doesn't really matter, right? We could have done from A to A plus epsilon. We can do, and here we do from A minus epsilon to A, but a point that is around A, that has width epsilon, And then we divide by epsilon, right? Because that's the point. The point is that you multiply the density by the length, and that gives you the probability. And that's the definition. Realize that this probability here, by what we said before, the properties of the CDF, that's just the CDF at A minus the CDF at A minus epsilon. And if you remember your calculus, this is exactly the definition of the derivative of the CDF, because the derivative gives you the rate of change of a quantity, in this case of the CDF. Okay, so when is the density going to exist? Precisely when the CDF is differentiable, which means that it can be approximated linearly at some point. So then the slope of that line is going to be the probability density. I really recommend that if you don't remember intuitively what derivatives mean and so on, go to Wikipedia just for 5 minutes and take a look, and this will actually help you a lot with the intuition. Okay, so imagine that you have a CDF like this one, which we had already talked about when we were talking about CDFs. Now I want to see what the density is, and here we're going to see that the density gives us, in my opinion, a much more intuitive view of what's going on with the random variable. What's going to happen around here? Here, the CDF is linear, so the density is going to be constant. So it kind of makes sense, right? As we go towards the right, because the CDF is linear, we're gaining constant amounts of probability, if you want, of being in that interval. Then, when the CDF is flat, here the CDF is constant, we don't gain any probability. We had already talked about this. So actually the random variable is essentially never going to be here. If you think of the density, because the CDF is constant, the density is going to be 0 there. So that actually tells us immediately. And then here it turns out that the CDF is quadratic, so the density is going to be linear. Okay, this is how the density looks like. Much more intuitive, right? Here immediately we see the random variable is never there. Here we see that the density is constant, and here we see that there is an increase in density as we go towards the right. Okay, so the definition again is that the density, so a random variable with CDF big F of A, has PDF equal to the derivative of the CDF if the derivative exists, which is what we mean by a function being differentiable. Okay. Remember that we had talked about a distribution that had a linear CDF, and we saw that in that case, the probability that the random variable was in an interval was exactly proportional to the length of the interval. So what's the density going to be equal to in those cases? It's just going to be a constant. And random variables, continuous random variables that have constant densities over a certain interval are called uniform random variables. We're going to be referring to those pretty often. It's a very natural thing to assume, right? You're interested in some random quantity that is can be in an interval, and you say, well, it has the same probability of being anywhere in the interval. That's captured by saying that the density of probability is constant. Because remember, we cannot define probability for individual points. Okay, so we're going to say that the uniform random variable on the interval AB is a random variable that has density 1 over b minus a. Realize that it has to be 1 over b minus a so that the probability of being between a and b is equal to 1. This actually brings us to something, to a point that is important, which is the density is not a probability. It's something that you multiply by lengths to obtain a probability. We already saw that probabilities cannot be larger than 1. So in particular, the CDF or the PMF can never be larger than 1. So let me ask you, can a PDF be larger than 1? And the answer is yes. If we go back here to the uniform distribution, and now we imagine that we have a uniform distribution, instead of between 0 and 1, between 0 and 0.5, the density, so that the probability of being between 0.0 and 0.5 is equal to 1, so that probability is equal to 1, the density between 0 and 0.5 is going to be 2. The uniform random variable between 0 and 0.5 has density 2, which is larger than 1. And that the reason is that the density is not a probability. It's something that you multiply, if you want intuitively, something that you multiply by length infinitesimally to build probabilities. Okay, so how do we use the PDF to compute probabilities? Because we have seen that it's kind of more intuitive to use than the CDF, so we will be doing a lot of that, of just defining the PDF and forgetting about the CDF, even though we know we can obtain it by integrating the CDF. Okay, so let's say that we're interested in computing the probability of the random variable being in an interval. We know that that's just the CDF at B minus the CDF at A. We also know that the PDF is the derivative of the CDF. So, you know, by a basic, I think it's the first theorem of calculus or something like that. I'm not very good with theorem names. But, you know, by basic calculus, this is just the integral from A to B of the PDF. So it's the area beneath the PDF between A and B. If you're interested in any other Borel set, so remember that Borel sets, this sounds really fancy, but they're just unions of intervals, possibly countably infinite unions of intervals, but unions of intervals nonetheless. If you're interested in the probability that the random variable belongs to such a set, then you can just divide the set into intervals. In fact, into disjoint intervals, because if some of the intervals are not disjoint, you just merge them together. And then you want to know the probability that A is within this Borel set B. You divide it into the union of intervals. We know, and if you don't remember, go back to the video on continuous random variables where we proved this, that if you want the probability that a random variable is in a disjoint union of intervals, you can just sum the probabilities that it is in each of those intervals. So we have that sum, and now this we know how to compute because of this, right? We just have to integrate the PDF. So we integrate the PDF on each of the intervals, and that amounts to just integrating over B. So long story short, if you want to know the probability that the random variable is in a certain set, you just integrate over that set. And as long as that's a Borel set, which means it's a union of intervals, which is always going to be the case for any reasonable example, then you are going to be able to integrate it, and you're going to get the probability. Okay, so here we are. We want the probability that this random variable is between 0.5 and 2.5. The probability is the area under the curve of the PDF that lies between 0.5 and 2.5. Here, remember that the density is 0, so there's no probability there. So we just have to add this guy and this guy, and that gives us the probability. Again, in my opinion, much quicker to visualize than what we're doing with the CDF, where you have to subtract the probability up until a certain point minus the probability up until another point. A bit less intuitive. Okay, so now we have to ask ourselves what properties is a PDF going to have, first of all, and second of all, are those properties sufficient to define a PDF? So it turns out that a PDF is non-negative and integrates to 1. So let's see why that is the case. Why do you think a PDF is non-negative? You might be tempted to remember, the CDF was non-negative because it was a probability, so maybe here too. Well, no, the density is not a probability, right? But it is related to the CDF. So if you remember, the CDF is non-decreasing. So its derivative cannot be negative. Okay, and that's the reason why the PDF is not negative. Why does it integrate to 1? Well, we've seen that the way we compute the probability of the random variable being in a certain set based on the densities by integrating over that set. Here we're integrating over the reals. Since the random variable is going to end up mapped, so the random variable, remember, maps outcomes to real numbers, it has to map to something. The probability of all the real numbers has to be 1. Okay, so that's why PDFs always integrate to 1. The question is, well, after we have established this, these are important properties to know, are these enough? Like if I get any function which is non-negative and integrates to 1, is it a valid density? And this is important because that's exactly what we're going to do, in fact, in the next video, to estimate PDFs from data. The answer is yes. This gets, so are those two conditions enough for a PDF to be a valid, for a non-negative function that integrates to 1 to be a valid PDF? The answer is yes. It gets a little bit complicated. I'm not going to go into the details, but the point is that you can build a probability space that corresponds to that density, and the way you do it is you take the reals as your sample space, you take your collection of events as the Borel sets, and now to assign probabilities, you just use the density by integrating over the Borel sets. Okay? I mean, this is just in case you're very mathematically inclined and you're worried, like, is there a probability space? So if you're worried about that, then this gives you an answer. All right, so let's finish by considering functions of random variables, because as we had discussed in the discrete case, this is really useful. You're modeling some quantity and then you realize that you're actually interested in a function of that quantity. So first of all, if I have a random variable A, and now I compute another variable B by applying a deterministic function to A, is that a random variable? There's two ways to answer this, right? One is the intuitive way. So you say, okay, look, A is uncertain. I don't know where it is. I can only say the probability that A is here, is between here and here is this. The probability that it's in this other interval is that. So if I apply a deterministic function to that, that's going to remain uncertain. So intuitively, it should be a random variable. Mathematically, it gets a little bit trickier, okay? The answer is yes, except in very weird cases. The reason is that, remember that mathematically, we have this probability space that we never really built, but we kind of know is there. And this guy maps outcomes to the real line. This would be the first random variable A. Okay, and the real line is going to be purple in this case. Okay, this is the real line. And now we know, because A is a valid random variable, that if we consider any interval AB, the preimage through A of this interval, this set here, has an assigned probability. So we're good. But now we have another function. So this was A. Now we have another function that maps from the reals to the reals. Okay, this function is G. Now this other real line is going to be weird looking orange. Okay, so we have this other line here. And now we have to worry about if we have an interval here, any possible interval, its preimage. So if its preimage, like here, let's say, its preimage through B, which is equal to G composed with A, is that preimage measurable? And it turns out that you can actually design G in a very strange way so that that doesn't happen. But this is really like very, very mathematical. Like you really have to, sit down and do it really carefully. And this is never going to arise, for example, if G is continuous or if G is just reasonable. So in most cases, that's going to be a valid function. If you're a mathematician interested in measure theory, then things get a little bit hairier. And I do encourage you to look a little bit into measure theory because it's some really cool math. Okay, so how do we compute? So let's assume that it is a valid random variable. These weird things don't happen. How do we compute the PDF of G of B? There are some formulas that are essentially derived in the way that we're going to do now. Instead of using the formula, I prefer to just go from first principles because like that I don't get confused. So what I like to do is to think, okay, I know that the CDF has an interpretation as a probability. So let me just compute the CDF of this new quantity. That's going to be easy because I just need to express the new quantity in terms of the old quantity, and I know the density of A, or I know something about A. And then I'm going to take the derivative of F. So I like to compute the CDF, again, because it has an interpretation as a probability, and then you can just differentiate it to compute the PDF. This is best illustrated through an example. So let's imagine that we know the voltage in some electrical circuit, and the voltage has a density that we know. But now we want to know the power, which is the squared over a resistor or something like that, which is the square of the voltage divided by R, where R is a constant. Realize that R does not have a squiggly thing on top, so you can think of it as a number, like 23 or something. Okay, so now what is the density of the power? We're interested in that. What we do is, we say, okay, we know about CDFs. We know that the CDF is just a probability, so that's going to be easier to compute. So what's the CDF of this new random variable at a certain point x? It's just the probability that it's more or equal to x. Okay? Now we don't have the PDF of x or anything about x, so that's the whole point. So what we're going to do is we're going to plug in our expression here. We're going to say this probability is just the same as the probability that the square of the voltage divided by R is more or equal to x. So then what are we going to do? We're going to integrate over that set that we're interested in. We want to know the probability of this. We know the PDF. We're just going to integrate over it. Okay, so we're going to integrate over all the numbers such that v squared divided by r is more or equal to x. That happens if v is between, so just to make sure, so we want v squared smaller or equal to x. When is this going to happen? It's going to happen when v squared is smaller or equal to rx, and that happens is if v is between minus, wait, I actually hate this color, I don't know why I chose it, but I'm going to stick with it, minus square root of rx, when v is between minus square root of rx and square root of x. And by the way, I really encourage you to do this on your own. Maybe I should have said it at the beginning, but you can always go back and try. So now we're just integrating over this, and that's the value of the CDF. We can stop here because we realize that now these are constants, okay? We can just differentiate this to obtain the PDF. Okay, so first of all, what is the... Oh, sorry, so this is for x greater than 0. For x smaller than 0, v squared, that cannot happen, right? So the probability is always going to be 0. Okay, the probability there is 0. You always need to remember to look at the full range of possibilities, and here it's covered by x greater than 0 and x smaller than 0. Okay, but now I got derailed. I was very excited. I had gotten the CDF for x greater than 0. So now how do I get the PDF of v? The way I do it is just I take the derivative. Okay, and again, by calculus, if you take the derivative of something, like you take the derivative of something, of an integral up to rx, basically the derivative is going to be this at rx multiplied by square root of r over x, and you also have to take the derivative at the other side. Okay, this comes from the fact that if you have, let me see if I remember my high school calculus, the derivative of this, if you go from minus infinity, is equal to, actually, wait, I should have written small f. The derivative here of f, let's say fa dA, from a minus infinity to x, this derivative is just f of x. Okay, so then we apply this to the previous expression, and we end up with this expression for the density of the power. The important thing is not the value of the expression itself. The important thing is you have another quantity, okay, which in this case was the power. You look for the CDF of that quantity. That's going to be a probability. The probability that that quantity is more or equal to a certain constant. You derive it with all the information that you have, and then you differentiate to get the new PDF, and that's how you do it. So hopefully that illustrated this. What have we learned in this video? We have learned the intuitive definition of the probability density function, then the formal definition as the derivative of the cumulative distribution function. We have used it to compute probabilities, and then we have seen how to compute the density of deterministic functions of random variables. Thank you very much.